All right, so we are going to be doing section 8.5 today. This is leading into probability eventually, but all we're talking about in section 8.5 is counting the number of ways that something can happen, that an event can happen. If we know that information, then later on we'll be able to calculate probabilities. But no probabilities today, just counting the number of ways. So here's my first little example. You probably, if you've taken the ACT or SAT, you've probably seen problems like this. Let's say you've got 2 jackets, 3 shirts, and 4 bottoms, and you want to, you're packing for a trip, and you want to try to pack lightly. So this is what you have chosen, okay? I want you to figure out how many outfits are possible. So, for example, you could say, okay, I'm going to take this white jacket and I'm going to pair it with this red shirt and shorts. I'll move that off to the side. So there's one outfit right there. I could keep the jacket and the shirt and use a skirt. There's a second outfit. Or these pants, that's a third outfit. Or these pants, that's a fourth outfit. Or I could switch shirts and do shorts for a fifth outfit, skirt for a sixth outfit, these pants for a seventh, these pants for an eighth. Or I can do the tank top. Here's a ninth outfit, 10th outfit, 11th outfit, 12th outfit. And then I can do the same thing with this jacket and match each shirt with each pair of pants. Okay, you get the idea? Now, there is something called this fundamental counting principle. I'm getting these out of the way. Down here, this fundamental counting principle, which says if events are independent, so like choosing a jacket is independent from choosing a shirt, is independent from choosing a pair of pants. If events are independent, then you can just multiply them to figure out the number of ways. So what that means is I can take 2 jackets times 3 shirts times 4 bottoms, and that will give me 24 different outfits. So that's the fundamental counting principle. When events are independent, when their probabilities don't affect each other, so the chances of me choosing a jacket has no effect on the chances of me choosing a shirt, has no effect on the chances of me choosing a pair of bottoms, then to find the number of ways they can occur together, you just multiply them together. And that's going to come up in some other problems that we do today. Now, you've seen this formula before when we were talking about Pascal's triangle. So, this is your formula for combinations. So, it's when you have n number of things, and you are going to choose r number of them. So you might see the word choose, you might see the word combination, and you can read this as n choose r. And here's your formula, but remember we can do it in our calculator. In your calculator, it's menu 5, 3, I believe. Let me just double check that real quick. Menu 5 is probability, 3 is combinations. Yep. And then in your calculator, it will give you like this. And then you have to fill in something, comma, something. So here's an example. Let's say you got 12 toy cars and you're going to choose 3 of them to let your little brother play with. So essentially you're going to just scoop up 3 cars. Any 3 cars. Doesn't matter the order, nothing. Just scooping up 3 cars. That would be 12 choose 3. Out of the 12 things I have, I'm choosing 3 of them. And when I go to type it in my calculator, I would do menu 5, 3. I would get this, and then I would do 12, comma, 3. And when you do that in your calculator, you're going to get 220 ways. there are 220 ways for me to scoop up 3 cars out of the 12 cars. And that's pretty crazy. I think the difficult part of this section is when you get an answer, they're going to seem absurd. They're going to seem way off of what you would predict. And that's what makes this unit a little bit more difficult, I would say. Oh, going back, I have it highlighted here, but I didn't mention it. This is when the order does not matter. So again, it didn't matter which 3 I picked up, just any 3. There's no order to it whatsoever. Okay, so here's another example. We've got a Powerball lottery. And in the Powerball, you have 5 white balls and you have 1 red ball. And these 5 balls are drawn from a pool of 59 white balls in a container. And then they have a different pool of red balls. They've got 39 red balls, and only one of those gets chosen. And the question is asking how many different combinations are possible. So the idea is, well, let's take the number of white balls and the number of red balls. And the idea is these are independent events. The probability of me choosing a white has no effect on the probability of me choosing a red. They're from 2 separate bins. They have no effect on each other. So we're going to multiply them together. That is going back to this counting principle. Okay, now how many whites are there and how many are we choosing? Well, there's 59 white balls and I'm choosing 5. Any 5, any order. The order does not matter for Powerball. It's simply just did you get the numbers, but any order is fine. And then with the red, there's 39 reds in the bin and I'm just choosing 1. So if I put those in my calculator and multiply, this is what I'm going to get. Okay, maybe instead of ways, I'll say possibilities. That's a lot of possible outcomes, right? So to win the Powerball is gonna be pretty hard to do. Okay. This one. We're forming a 12-member team, and we've got 10 girls and 15 boys that we are choosing from. The team has to have 5 girls and 7 boys because it's a 12-member team, right? 5 girls, 7 boys makes 12 people. How many different teams are possible? Well, I'm going to have girls and I'm going to have boys. Those are independent events. Me choosing girls has no effect on me choosing boys, so I'm going to multiply. Again, that fundamental counting principle. So how many girls do I have to choose from? I've got 10 girls, and how many girls am I choosing? I'm choosing 5. Move on to the boys. How many boys do I have to choose from? Got 15 boys to choose from. How many do I want to choose? 7. Throw that in your calculator and you are going to get this. Okay, so this is the amount of teams that are possible to make that consist of 5 girls, 7 boys from that pool of kids. See, it's hard to estimate because it's so much off of what you would ever imagine. Okay, poker. How many 5-card hands are possible? 5-card hands, any 5 cards out of the deck. The order doesn't matter, it's just any 5 cards. Okay, well, how many cards are there total? There's 52 total cards. Okay, so out of those 52 cards, I'm just choosing 5 of them for my poker hand. So 52 choose 5. again, maybe I'll get my calculator up just to show you. I said it, but maybe just to show you how to do it in your calculator one more time. You're going to do menu 5, 3. Give it a second. Okay, here we go. Menu 5 is probability, 3 is combinations. And then we're going to type in for this problem, it was 52, choose 5. So I'm going to do 52, and then I'm going to do this comma, and then 5. And that is our answer. Oops, my pen got a little off there. I'll start over here. $2,598,960 possible hands. Okay. Let's see what else here. Okay. A company wants to hire 2 positions. 5 people apply. 2 are men, 3 are women. How many ways is it possible to not hire a man? So the wording here is a little weird. Not hire a man. So we're not even considering these 2 men. So how many women are there? There's 3 women. How many people am I trying to hire? I'm trying to hire 2 people. Okay, 3 choose 2. That's it. Put it in your calculator. You get 3. Okay, so it seems like a complicated problem. It's just kind of trying to trick you, like they're giving you extra information. So if we're not hiring a man, that means we're only, our total is only out of the women. So we only have 3 people to choose from, and we're choosing 2 positions. All right, now this next topic is called permutations. Okay, and here is the way that we would write it. NPR. This is when order matters. Okay, so if you have n things and you want to arrange them if you want to arrange r number of things out of n total number of things, then you would use this formula. So it's when you are arranging, you might see the word arrange, you might see things talking about order, but you're going to have to get that sense that there is an order. So here's an example. Let's say we got 12 people running in a race. How many ways can they finish first, second, and third? See, now this has an order. First place is different than second place, is different than third place. First place has more importance, maybe, than second or third. Maybe first place wins more money or a better prize than second or third. Or there's more weight to it or something like that. When there's an order to it, then we use permutations. So this would be 12p3. Now, in your calculator, if you go menu 5 for probability, then do you see how number 2 is permutations? So you get NPR, and we are doing 12p3, so we're going to do 12, comma 3, and you will get 1,320. So this was menu 5, 2. This comes up like if you ever go to Canterbury Park and you're bidding on horses, or if you, I don't know, have like a horse race party or something like that. You can place bets on them placing first, second, or third. So this is kind of getting into that idea of that if you have 12 things running in a race, there are 1,320 different ways that these horses could come in either first, second, or third place. In this case, it was people, not horses. All right, this is something that you might see on the ACT or SAT. How many ways can 7 people be seated in 7 chairs? When people read this question, they automatically think 49. And I know why you're doing that, but 49 is way off. Way off. Okay, because you have to think about the fact that this person right here could go into any one of those chairs. This person can go into any one of those chairs. But the idea is when one chair is full, then you only have, okay, for example, let's say we start with this first chair. And let's say this dude right here goes and sits in the first chair. Okay, so that guy is done with now. Now there's only, you see how there's only 6 people left that can possibly go in this chair? Okay, so from the beginning, before he chose that spot, how many ways could this chair be filled? There would be 7 ways that this chair could be filled. Any one of these 7 people could sit in that chair. Then when this kid sits there, okay, that seat's taken. Now, how many ways can this seat be filled? Well, there are 6 people left, so there's 6 ways that this chair could be filled. Let's say this cowboy dude sits in there. How many ways now can this chair be filled? Well, there's 5 people left. Maybe this little Bo Peep girl goes and sits there. Okay, now this chair can only be filled 4 different ways because there's only 4 people left. Maybe this guy sits there. Now you get the idea. This chair, there's only 3 people left. Only 3 ways that can be filled. Maybe she sits there. This chair, there's only 2 ways it can be filled. Maybe this guy sits there. And now there's only 1 person left that can fill that chair. And we multiply all of these together. Okay, so you have 7 times 6 times 5 times 4 times 3 times 2 times 1, and you will recognize that that is 7 factorial. Okay, now another way to do this would be the fact that we have 7 people and we are ordering them in 7 different ways. 7 of the people are getting ordered or arranged out of 7 total. Now, if you follow your formula for permutations right here, it's n factorial over n minus r factorial. So this number right here on top, factorial, and then this minus this on the bottom, factorial. So that would be 7 factorial, this number right here on top, and then 7 minus 7 factorial on the bottom. Now, that would be 7 factorial over 0 factorial. And I don't know if you remember, but 0 factorial is 1. It's defined as 1. So, do you see how we end up with 7 factorial? Just like I got here. So, I can do this problem. I can do it as 7p7. And when I type that in my calculator, I'm going to get 5,040 ways. That's the same thing as 7 factorial. Okay, so do you remember when we first started this problem and I said that a lot of people when they see this, they think the answer is 49? Do you see how 49 is way off? I can have different arrangements of 7 people in these 7 chairs and it would be 5,040 ways. It's crazy. It's hard to even predict. All right, this is the last example. All right, so how many orders can 5 girls and 3 boys walk through a doorway single file? So if it's single file, then it's kind of like the order matters, right? Someone's first, someone is second, someone is third. Now, what if there's no restrictions? That means that it doesn't matter if girls are next to boys. That's what no restrictions means. So I have 5 girls, I have 3 boys. That's a total of 8 people. And I'm ordering 8 of those 8 people. So 8P8. Just like the last problem, 7P7. I've got 8 people, single file, walking through a door, no restrictions. That's going to be 40,320 ways. Okay. Now, what if the girls are going to walk through before the boys? So we're going to have girls first, boys second. Okay. Now, girls, that stuff doesn't have an effect on the boys. Those are independent events. So I'm going to multiply. Now, I am ordering 5 girls. I have 5 girls, and those 5 girls are going to get ordered. And then out of the boys, I have 3 boys, and all 3 of them are going to get ordered. When I type that in my calculator, I'm going to get 720 ways. And this is less ways because there's more of a restriction now. The girls have to walk before the boys. So there's going to be less different possibilities when there's a restriction placed on it. Now, this is different. I just want to go back up to this problem right here. This is not 8 choose 8. Okay? If it was 8 choose 8, that would be saying I have 8 things and I'm going to choose 8 of them. I have 8 things and I'm choosing all 8 of them. I'm scooping up all 8 of them. How many different ways are there to do that? There's only one way to do that. Okay? We're not picking 8 people out of 8 people, that sort of thing. We're ordering them. We're putting them in a line and they're walking single file through a doorway. So anytime there is an order, it's a permutation. Okay? So if there's a hierarchy, if there's prizes involved, if it's anything to do with ordering like this, it's a permutation. Combinations, let's go back there. Combinations is when order does not matter. You're just choosing things or you're grabbing things, a handful of things or something like that. So that gets tricky, trying to distinguish between it's a combination or a permutation. And that's what your homework is going to focus on today. Come to office hours if you're having any trouble. And if the homework doesn't go great, then I will address that next week too. All right. Have a good day, guys.